Hey everyone, it's Aniruth, and this time we are going to be talking about something a little bit different. Specifically, we're going to be talking about the hint here, which is that we only need to check the factors until the square root of n. And this might be something that you're already familiar with. If so, great. If not, I'm hoping that I can maybe explain. And if you're thinking, well, why do I even need to know this? It's already given to me as a hint. I can just use it and solve the question and keep moving on. Well, I think that there are a couple of reasons why. The first one that comes to mind is if you're ever in a coding interview and they give you a difficult question to solve, maybe in fact you are asked to find prime numbers, one of the things that they might be looking for is efficiency. And you knowing that you only need to check the factors until the square root of n and why that's true might be something that helps you stand out and might be what they're looking for. In fact, I think the sort of thinking about these optimization tricks and techniques and when you're checking for conditions and things like that more generally is very useful because it helps you write better code, more efficient code, which I think there's really just no drawbacks to, unless it's too complicated and doesn't make sense to anybody. But this, I promise, will make some sense. So I think that there's a couple ways to explain this, and I want to start with thinking about factors. Specifically, I want to think about pairs of factors. So one way that we can rethink what it means to be a prime number is that we only have one pair of factors, and that this pair of factors is 1 and itself. And this is true for any number, right? In the sense that any number is divisible by 1 and itself. I could take the number 1000, I could take the number 6. It doesn't really matter what the number is, it will always be divisible by 1 and itself. And if I multiply 1 by itself, I get that number. But if I think about other numbers, let's say I take the number 6. Well, 6 has two different pairs of factors, right? So 6 has two different pairs. And those pairs are 2 and 3, 1 and 6. But in order for it to be a prime number, it can only have one pair of factors, 1 and 6. For example, if I take 7, which we talked about earlier was being prime, 7 only has one pair, which is 1 and 7. No other numbers, or whole numbers at least, divide it evenly. And if we think about this, then the reasoning for why we only check until the square root of n begins to make a lot more sense. Let me explain. There's a couple different formal proof techniques we could use, but I'm going to first start with just generally saying that if we write out what the square root of 6 is, well, I know that the square root of 6 is somewhere between 2 and 3. Why do I know that? Well, it's because 4 is less than 6, which is less than 9, which means that if I apply the square root, the same relationship of one number being less, like if I say 5 is less than 35, if I take the square roots of each number, it should still hold true. This means that 2 is less than the square root of 6, square root of 6, which is less than 3. So I know that the square root is somewhere between 2 and 3, but generally speaking, since we're doing less than or equal to, we don't need to actually go above the square root of 6, so we don't actually need to check 3. We literally just need to check 2. And the reasoning as to why you can sort of think this is true is I can rewrite these pairs like this. I can write 1 and 6, and I can write 2 and 3. And all I'm doing is checking of the existence of a pair. And to check the existence of a pair, if I check 2, that implies that there is some other number that 6 is divisible by. Now, we don't care what that other number is. We don't care what the other factor is. The very fact that 6 is divisible by 2 means that we've already checked this 3. We've already checked the other factor in the pair. And we can generalize this, right? If I take the number 91, for example, and I'll spoil a surprise and I'll go ahead and tell you that 91 is actually not a prime number. 91's factors are 7 and 13. Well, you just need to check up until 9. And the reason why is that, again, if I do the same logic, if I take 81 is less than 91 is less than 100. Why am I taking 81 and 100? Well, those are perfect squares, and we know what those are. We know that it becomes 9 is less than the square root of 91. I'm sorry, I don't know why I keep typing art. Maybe this is a piece of art, who knows? Many people describe math as an art, So we now have it going up to 9. And again, we can check going using the same sort of pairs. We know that one pair is going to be 1 and 91, but the other pair is going to be 7 and 13. And since we already hit the 7, it means that we don't need to keep checking. Now you might be thinking to yourself, well, hey, I know that these numbers are not prime numbers, and we already checked the 2, we already checked the 7. Like no matter if the stopping condition is x is less than n, or if it's x times x is less than or equal to n, it doesn't really seem to matter that much because, well, we already know that it's not going to be prime. Well, the real application is it saves you a lot of time when you don't have to check unnecessarily. Let's say I take the number 93, which I will spoil the surprise for you, is prime. So again, using the same logic, I don't know why. Oh, I have to come here. If I take the same logic as to 81 is less than 93 is less than 100, and then 9 is less than the square root of 93. I actually don't know why that's happening. I keep typing art, but if I take 9 is less than the square root of 93 is less than 10, well, I spoiled the surprise and I told you that 93 is a prime number, which means that I can check every number from 1 all the way to 92. Or actually not, I should not be, it does not matter if I check 1, technically it'd be 2 to 92. I'm only bringing up the 1 because it's useful to think about the factor pair. But instead of checking every number between 2 and 92, well, using the same concept of factor pairs, I know that I'm going to have 1 and 93 no matter what, but I don't need to keep checking all these other numbers, right? Those are the numbers between 2 and 92. Instead, I can just call it quits when I hit 9 and I realize that 93 is not divisible by any of those numbers, because if it were divisible by any of those numbers, then you would know that the other numbers would be divisible. That might sound kind of complicated, right? But I guess sort of the general intuition comes all back to that factor pair. If none of the numbers between 2 and 9 work, well, those are the ones that go on the top part of the factor pair. But if these don't work, then there is going to be no corresponding values, which means that we don't need to check, right? It all goes back to this idea of like the 2 and 3 with 6. Because I know that 6 is divisible by 2, I know that 3 is also going to be there in the factor pair, right? And the reason why that matters is because 6 being divisible by 3 means that it's not a prime number. But the point here is I don't need to check any of these numbers because I know that 93 is not going to be divisible by them, because if 93 were divisible by them, it would also be divisible by these. So checking this means I've already checked this. So I hope that it's a little complicated when you're first thinking about it. I would strongly encourage you to try this out on your own. It'll save a lot of time in the algorithm. But if you wanted a more formal mathematical proof, there's a couple of ways to do it. I think that I'm not going to go too far into it because it's not, I would say, like the most important part. But if you have two numbers that that multiply to get some number. If I say that n is some number which is equal to a times b, and I know that a and b are two whole numbers, well, it must be the case that a is less than or equal to the square root of n, or b is less than or equal to the square root of n. Because if a was greater than or equal to the square root of n and b was greater than or equal to the square root of n, then a times b, actually I can write this out if that's too much. So if I say a is greater than the square root of n, and b is also greater than the square root of n, then that means that ab is going to be greater than n. And if ab is greater than n, then n can't be ab. So we know that if a's can be at max square root of n and b can be at max square root of n. So this is sort of the intuition for why the factor pair sort of wraps around from 2 to 3. But yeah, that is sort of why this is true. This is kind of a long explanation. If it still doesn't make too much sense, that's totally fine. Thinking about it in terms of the factor pair will probably be a little confusing at first, but yeah, that is how this works. One last thing I'd like to point out is if you're wondering why we even check for this, right? Like I said that every single prime number or every single number, in fact, is going to be divisible by 1 itself. Why do we even include the factor pair? Well, it's sort of similar to the reason why we go straight to 2 and we check till it's 1 less, right? It's the reason why we do 1 is less than x is less than n, and we don't do equal or equal here, right? Is because we already know that those are divisible and that they exist as a factor pair. But it's not very useful in determining whether or not something is a prime number, because the prime number definition is that that's the only pair that exists. I hope this was useful. It was a lot of information within these last 10 or 11 minutes. But yeah, as I said earlier, I strongly encourage you to try your own examples, write out the factor pairs, see where it wraps around. And if you're trying out a prime number, see how much time it would save you and how many numbers you have to check.